Today, we're going to talk about a pretty wild new idea in physics. It's a theory that claims it can solve some of the biggest mysteries out there, not by adding new weird stuff to the universe, but by completely changing how we think about the very fabric of space itself.
So let's just jump right in with a massive question. For years, we've all heard that something like 95% of the cosmos is made of mysterious dark matter and dark energy. But what if that's just wrong? What if the problem isn't the universe, but our fundamental understanding of gravity?
To really get why a new theory might even be necessary, you have to appreciate the size of the hole in our current understanding. Right now, physics is staring at two gigantic gaps in its knowledge, and together, they make up almost everything in the universe.
In this chart right here, it lays the problem out perfectly. Everything we see, everything we've ever touched or studied, stars, planets, galaxies, us, all of that is just a tiny 5% sliver of what's out there. The other 95%? It's a complete mystery, split between these two things we've labeled dark.
So what are these two mystery ingredients supposedly doing? Well, dark matter is like the universe's invisible glue. We see galaxies spinning so fast they should be flying apart, so we've had to invent some unseen mass that's holding them together. And dark energy? It's doing the exact opposite. It's pushing the universe apart, making its expansion speed up. So you've got two giant, unknown forces basically running the whole show. All right, so how on earth do you solve a problem that big? Well, there's a radical new idea on the block called dynamic vacuum field theory. Let's call it DVFT for short. And it suggests we don't need to solve it because the problem isn't really there. It proposes a whole new foundation for physics that might just make these mysteries disappear. You see, at the very heart of modern physics, there's this deep, fundamental split. We use Einstein's general relativity for the big stuff, planets, stars, galaxies. But for the tiny, subatomic world, we have to switch to a completely different set of rules, quantum mechanics. And for 100 years, trying to get these two to play nice has been the holy grail of physics. DVFT's solution begins by challenging one of our most basic assumptions. It says the vacuum of space isn't nothing. It's not empty. In fact, it's the most fundamental thing there is, a vibrant physical field that fills literally everything. I want you to picture this vacuum field like a deep cosmic ocean. It's everywhere, and it has actual properties like density and stiffness. In this picture, a particle, like an electron, isn't a little ball, it's just a localized ripple, a little knot of energy in this ocean. And gravity? Gravity is just how the ocean itself warps and bends around these ripples. And this is the real game changer, the big idea. DFT says we've been making a huge mistake looking for one single master equation for gravity. Gravity isn't one thing. It's what we call an emergent behavior. This one single vacuum field just acts differently at different scales, and that creates what looks like four separate versions of gravity. So let's get into the heart of this. How can one single field give you four different results? Well, think about water. It's always H2O, right? But depending on the temperature and pressure, it can behave like solid ice, liquid water, or a gas like steam. Same stuff, different behaviors. Okay, this is where it all comes together. Look at this. At the tiniest quantum level, gravity is just a function of the vacuum's density. In our own solar system, the theory's equations simplify perfectly to Newton's law of gravity, which is why our existing model works so well close to home. But here's the magic. When you zoom out to the scale of a whole galaxy, where things are way more spread out, the vacuum behaves differently. The equation changes, and gravity becomes stronger than we'd expect. And on the largest cosmological scale, the vacuum's own leftover energy naturally pushes space to expand faster and faster. It's one field behaving in four different ways depending on the scale. This really gets to the core of it, doesn't it? It's a total paradigm shift. We've been trying to force this one-size-fits-all equation for gravity onto the entire universe. DVFT just says, nope, gravity is smarter than that. It adapts to its environment. So let's circle back. If gravity can change its behavior, what does that mean for our big mysteries? What happens to dark matter and dark energy? Well, for dark matter, the solution is just elegant. The whole problem was that galaxies spin too fast. The gravity from their visible matter shouldn't be enough to hold them together. But DVFT's galactic scale equation shows that in these low-density regions, gravity just naturally gets a boost from the vacuum field itself. The extra gravity we need is already there, woven into the fabric of space. You just don't need dark matter anymore. And what about dark energy? The theory says this vacuum field has a sort of minimum energy level, a baseline buzz of energy that's always there. And this tiny bit of residual energy, when stretched across the entire cosmos, acts like a gentle repulsive force. It naturally pushes the universe to expand at an accelerating rate. Again, it's not some mysterious new energy. It's just a fundamental property of space itself.
Okay, so you're probably thinking, if this theory solves everything, why haven't I heard about it? Well, that's because it is brand spanking new. And science, rightfully so, demands an incredible amount of proof before it accepts a revolution.
And this is some really crucial context. This idea was only proposed in late 2025 by Satish B. Thorway in a manuscript he published himself. Right now, as we speak, it has not gone through formal peer review. It hasn't been widely accepted by physicists. It's an idea in its absolute infancy, getting some buzz online, but it's very much on trial.
But, and this is a big but, what makes this compelling, what makes this real science, is that it's testable. DVFT makes specific, concrete predictions about things we can actually go out and measure. It predicts weird patterns in the afterglow of the Big Bang, new kinds of gravitational waves, and even that the first galaxy should have formed faster than we thought, which, by the way, is something data from the new space telescope seems to be hinting at.
So we're left at this incredible crossroads. Is DVFT a tantalizingly complete picture of everything, unifying physics with one beautiful idea? Or is it a fascinating blind alley? The truth is, we don't know yet. It has to pass the brutal tests of the scientific method. The next few years of experiments will tell us if this is the breakthrough we've been waiting for or just another beautiful idea. The search definitely continues.